Okay, we've seen trees, we've seen binary trees in particular, and especially we've seen search methods on trees, depth first and breadth first. We've seen that we can use that to find out whether something's in a tree, but we can also use it to trace the path that gets us to a particular point in a tree. And that led to this nice idea of decision trees, a way of finding a solution to an optimization problem like our knapsack problem, where we can find a good solution by simply exploring either explicitly or implicitly the tree of solutions. You'll come back to this idea of knapsacks and other optimization problems in the second half of this class, but we wanted you to see how trees would actually help with thinking about those kinds of problems. Let's do one last thing with trees. What happens if our trees are overgrown? Bad pun, but what it means is we've been implicitly, and in fact I would even say we've been explicitly assuming that there are no loops in our trees. Remember we said that a child has at most one parent, or has one parent in fact. We also in essence were saying that no node has or is the parent of a child closer to the root, that the children always lay below. What if we relax this constraint? Well, the relaxation starts leading towards a wonderful generalization called a graph. Graphs are used everywhere in terms of solving all sorts of important problems. We're going to come back to graphs in the second half of the class. But for now, we can think about relaxing this constraint just to explore the idea of how simple changes to the code would let us deal with loops and still preserve the behavior we would like. Let's build an example. Here's my tree from before. I've added simply one new connection. That 3 is the parent of the root. Remember, before the root had no parents. Here now, 3 is the parent of the root node 5. What would happen if I tried to search in here? Well, let's think about this. We can do depth first binary search as we did before. Let's start at the node n5, and let's look for 2. So find 2 is just a function that's going to tell us whether the value of the node is 2 or not. Oh, and it looks at 5 and then 2 and says, I'm done. Okay, that sounds good. What happens if we do breadth first search? Same thing. Same amount of work finds the solution. Okay? Depth first search, starting at M5. Remember, previously we were looking for 6. This doesn't look good. In fact, maybe you've seen this. I'm in an infinite loop. And you can probably see why. Depth first is taking this path. Oh. And there's no way to break out of that path. I'm never going to find 6. What about breadth first? Oh, well, it still found it. And that's good because it was doing this kind of search, and it got there before it ever hit the loop. And even if the loop had been earlier on, because I'm moving down the tree stage by stage, breadth first is probably still going to find it. So that sounds pretty good. So maybe breadth first is okay here. All right, so now we're going to say, starting at N5, look for 10. Oh, goodness. I'm back into that infinite loop. And that makes sense because this loop here is going to create an infinitely deep tree, and I'm never going to find my way around it. Okay, so to summarize this a bit better, if we run depth first in this kind of tree, we've already seen it. We're going to get an infinite loop, and in many cases, even when the item's present, we're always going to get it if the item is not present. And for breadth first, it's going to be less efficient. It will still work if the item's present. It will still find it, but it's not going to work if it's not present, and that doesn't help us any.